In the previous lecture, I discussed the lift force. This lecture will be about the drag. I hope you remember the formula for the lift force. This force is equal to the product of a number of parameters. These parameters are the lift coefficient, the air density, the air speed, and the wing surface area. We also have seen that the lift coefficient is dimensionless. For the drag we have a similar formula. The only differences are that the lift force L is replaced by the drag force D and that the lift coefficient is replaced by the drag coefficient. The structure of the formula is the same. Also, this coefficient is dimensionless and the other variables have the same meaning as in the equation for the lift. The drag is composed of several contributions. One way to split the drag is to look at the profile drag and the parasitic drag. The profile drag is related to the wing surfaces and the parasitic drag to the other sections of the aircraft, like the fuselage, undercarriage, etc. In the second way, the profile drag can be further split into pressure drag and friction drag. The pressure drag is the resultant force when we take the integral of the pressure over the wing profile. The friction drag arises when the air has contact with the skin surface of the wing. In this slide, you can see different types of drag. First, we have the skin friction, when the air glides over the wing surface. Secondly, we have the pressure drag, creating pressure differences and inducing a turbulent flow and vortices. Then there is the wave drag, which is the drag induced by shock waves of an aircraft. Look at the shock waves for this fighter jet, which become visible due to condensation of air. This type of drag is specific for transonic and supersonic flights. Finally, we have the parasitic drag of all components not contributing to the lift of the aircraft. Often the drag coefficient is split into a component which depends on the lift coefficient, the so-called induced drag, and a component independent from the lift coefficient, the CD0. To explain the difference between the friction drag and the pressure drag, I ask you to look at the following pictures. From the left to the right, you see an increase in pressure drag and decrease in friction drag. Pressure drag is a drag which acts perpendicularly to the surface of an airfoil. The friction drag acts in parallel to the surface of the airfoil. So far, we looked at two-dimensional images of wings or cross-sections of wings. Implicitly, we assumed that the wings had an infinite length. In reality, though, the wings have a limited size, and there is an added effect if we look at three-dimensional wings. Over the wing, the air pressure is reduced. Under the wing, the pressure is slightly increased. At the wingtip, the high pressure from the lower surface will curl around the wingtip to match the low pressure at the upper skin of the wing. This generates vortices which may also cause significant drag forces. In order to reduce the size of these vortices, nowadays winglets are installed at the wingtips. These winglets may reduce the drag of an aircraft by 3 to 6% and result in significant reduction in fuel consumption. This reduction might be used to increase the range of the aircraft. When we bring the lift curve and the similar drag curve in one plot, we see the lift curve which is nearly linear up to its maximum. The drag curve is an exponential curve, since the induced drag is proportional to the lift coefficient squared. Note that each curve has its own vertical axis and that the lift coefficient is roughly 5 times larger than the drag coefficient. If we use the CL and CD curves, we can construct a so-called lift-drag polar. In this curve, the lift coefficient is plotted as function of the drag coefficient. From such plot, the most efficient flying condition can be retrieved. That is, the point with the highest CL-CD ratio. This ratio can be found by drawing the tangent to the curve. So the maximum CL-CD ratio is called the glide ratio. Why is this value important? This ratio is interesting for the design of an aircraft. For optimum flight, one would like to stay as close as possible to this ratio, because at that point, the drag is minimum for a given flight. So the fuel consumption is the lowest in that case. To give you an idea about the glide ratios of some aircraft and some birds, look at this list. Sailplanes and aircraft with slender wings like the U-2 reconnaissance aircraft have very high glide ratios. Also, the glide ratio for a Boeing 747 is still high. On the other hand, the space shuttle flies like a brick. It has a very low glide ratio. Note also the glide ratios for the birds, in particular the albatross, which is a superb glider. This bird also has a low weight, which gives the bird excellent flying properties over long periods of time. To conclude, this lecture we looked at the drag forces acting on an aircraft. These should be as small as possible. The drag comes from many sources. Some of them, like tip vortices, can be reduced. In the last lecture about forces on aircraft, we will look at the weight and thrust forces.